Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today we are going to discuss introduction of spectroscopy. The word spectroscopy is widely used to mean the separation, detection, and recording of the energy changes involving nuclei, atoms, molecules. These changes are due to the emission, absorption, or scattering of the electromagnetic radiations or particles. In most branches of spectroscopy, the system interacts with the electric field. However, in case of magnetic resonance spectroscopy, it interacts with the magnetic field. The experimental application of spectroscopic methods in chemical problems are diverse, but all have in common the interaction of electromagnetic radiations. As a result of this interaction, energy is absorbed or emitted by the matter in the form of quanta or photons. Electromagnetic radiation behaves like waves and the particles. For example, refraction, when electromagnetic radiations passes from one medium to another, are explained best by describing electromagnetic radiation as a wave, while other properties such as absorption and emission are better described by treating light as a particle. Electromagnetic radiations treated as alternating current in space associated with mutually perpendicular electrical and magnetic component are and also perpendicular direction of propagation. Regions of electromagnetic radiations, here is the increasing order of their wavelengths, that is from gamma rays, X-rays, UV visible, IR, microwave and radio waves. Wavelengths ranges from thousands of kilometers down to the fraction of size of the atomic nuclei, and while the increasing order of the energies of the electromagnetic radiation is the reverse, that is radio waves, microwaves, IR, visible, UV, X-rays and gamma rays. Energy of the photons ranges from 1.24 mega electron volt to 12.4 femto electron volt, and the frequency ranges from 1 Hz to the iota Hz. Gamma rays belongs to the transition in nuclear transitions. X-rays used for the core electron transitions, UV visible for the valence electrons. In IR, we study the vibration of the molecules, and microwaves used for the electron spin resonance, and radio waves for the nuclear spin resonance. Some basic terms in spectroscopy. Wavelength. The distance between two successive crests or troughs of a wave is known as wavelength. It is denoted by the lambda. It is measured in units of the length such as centimeters, nanometers. Wave number. Wave passes through a unit distance. It is denoted by the nu bar, and that is the reciprocal of the wavelength. Frequency. Number of waves that can pass through a point in 1 second is known as frequency. It is denoted by the nu and its unit is hertz, and it is equal to reciprocal. It's inversely proportional to wavelength. Energy. Energy is equal to h nu, and which is equal to hc over lambda, where h is the Planck's constant and c is the velocity of light, which is equal to 2.998 times power 8 meter per second. Interaction of electromagnetic radiations with matter. If radiations possess the appropriate energies absorbed by the matter, and as a result electronic transition, for example in UV visible spectroscopy, rotational transition, for example in rotational spectroscopy, vibrational transition, for example in IR spectroscopy, atoms and molecules becomes excited and lose energy by losing in the form of heat or by re-emitting the electromagnetic radiations. Sometimes a portion of the electromagnetic radiation that passes through matter, instead of being absorbed, may undergo scattering or reflection, or may be re-emitted at the same or different wavelengths. When electromagnetic radiation is neither absorbed nor scattered, it may undergo changes in orientation and polarization. Absorption and emission. In absorption, a photon is absorbed by a nucleus, atom or a molecule which undergoes a transition from ground state to a excited state, and in emission re-emitted at the same or different wavelength, the type of transition depends on the energy of photons. Here, if the incident radiation have the energy which is equal to the difference of energy between ground state and the excited state, as a result, this energy is absorbed and the electron of the atom or a molecule will move from ground state to the excited state. And same is the case when the electron comes from excited state to the ground state, it will emit the equal amount of energy which is equal to the difference of energy between ground state and the excited state. Absorption laws. Beer-Lambert's law. The Beer-Lambert law states that the quantity of light absorbed by a substance dissolved in a fully transmitting solvent is directly proportional to the concentration of the substance and the path length of the light through the solution. Let's try to understand this concept with the help of the animation. Now we try to understand the Beer-Lambert's law with the help of this animation. Here our sample is mixture of the drinks. Its concentration is 100 millimolar and the preset wavelength is 508. Let's we start with by giving the source radiation. Here it shows the transmitter is 31.19% and absorbance is 0.51. Now check the absorbance for the black solution. 0 millimolar concentration of the mixture of drinks and absorbance is 0, wavelength is 508 nanometer. As we increases the concentration from 0 to higher, you see the absorbance also increases. As we increases the concentration, absorbance increases. As we decreases the concentration, absorbance decreases down to the zero concentration, zero absorbance. Let me discuss another example. For example, cobalt. Here preset wavelength is 540 9 nanometer, concentration 100 millimolar, absorbance 0.47. As we decreases the concentration, absorbance decreases. For blank solution, absorbance is 0. As we increase the concentration of the sample, absorbance increases. For 100 millimolar concentration of cobalt nitrate, the absorbance is 0.47. So, according to the Beer-Lambert's law, absorbance increases by increasing the concentration of the sample. Now we change the path length of the sample. As we increases the path length, absorbance increases. As we decreases the path length, absorbance decreases. You see here the preset wavelength is constant, 549 nanometer, concentration in 100 millimolar cobalt nitrate. We are changing just the path length. As we increases the path length, absorbance increases. As we decreases the path length, absorbance decreases. Nickel chloride. Preset wavelength is 433 nanometer. For 100 millimolar molar solution, absorbance is 0.48. Once again, we are changing the concentration, decreasing the concentration down to the 0. In blank solution, absorbance is 0. As we increases the concentration, absorbance increases. Now we study the Lambert's law. As we changes the path length, absorbance also increases. Here wavelength is constant, concentration is constant, but we are changing the path length. As we increase the path length, absorbance increases. As we decrease the path length, absorbance decreases. So hence proved, absorbance is directly proportional to the concentration and the path length, according to the Beer-Lambert law. Here we can also verify the concept of the lambda max. You see, for 100 millimolar solution of the nickel chloride, preset value of the wavelength is 433 nanometer and the absorbance is 0.53. As we increases the wavelength, absorbance decreases. As we decreases the wavelength from preset value, absorbance also decreases. At 433 nanometer, it shows maximum absorbance. The wavelength at which the sample shows maximum absorbance is known as lambda max. Thanks for watching. Please like and subscribe our channel for more videos. Take care. Allah Hafiz.